The microstrip patch as more specific meta element, totally a new concept I'm going to disclose today in this conference, and with a quick recap. Microstrip antenna, you know, it started its journey long ago, but in practice, in reality, it is in early 80s. So one group, they tried to feed the antenna not from its conventional mode or conventional side, they tried to feed it from side. And in doing this, they estimated one interesting parameter, that is their pole to cross pole. And they mentioned two polarizations based on their feeds from two sides. So from that investigation, one interesting point was picked up by Professor Kai-Fong Lee and his group at the time. The subsequent year, it is 1988, they particularly pointed out very interesting feature of a microstrip patch, particularly it was for a rectangular patch. That is, the orthogonal mode is the source of cross-polar radiation. They specifically mentioned, they calculated and presented the results. But this paper, when you are going to read it, you should be very careful because they use no specific diagram. They refer to one previous diagram, so it is not in conventional style. But within 4 years' time, they developed their study and more mature result they presented in 1992. And actually, it is very close to today's mode of presentation, what we do nowadays. And I see Professor Lee, his students, Professor Luke, and another co-author, P. Cam. They calculated the cross-pole and cross-polar radiations in a different form. And based on their estimation was based on the higher order mode over the orthogonal axis. Immediately after that, the antenna community started working on different engineering, some additional things to mitigate the cross-polar radiations, because cross-polar radiation is not very desired or healthy thing for a microstrip patch. So I'm going through a very quick recap, and then I'll address the main problem. The engineering, if you look at, they're in different categories. One is feeds, ground plane shaping, effective ground structure integration technique, some perturbation in the cavity by edge shortening. So you can categorize the technique makes basically in four. Differential feeds. So it is not very straightforward, because we need a couple of feeds, and the phasing should be 180 degree out of phase. So another feed network you need, but they're working very well. The cross poles immediately goes down by more than 10 degree. And this technique you see nowadays, so in many works you will see the differential feeding one good technique, but you need that kind of engineering feed. Even with the single feed, you can manage your cross-polar radiation, and this report is quite interesting, and you can see this one in one transactions paper in 18 in detail. I just give you one interesting point. that whenever we design our microstrip patch, most of the time we do one mistake and it is our convention that normally its band works over where its resonant resistance is falling, that is in downward journey, downward trend. And during that frequency band, in this frequency band, the cross-pol increases. So our investigation shows this cross-pol actually is much below if we go in the lower side of the spectrum and where the resistance is increasing. The physics, everything you can find in this work. So only engineering we need that our impedance should be shifted to the left. How? That is kind of capacity feeding. So it is not that complicated. So you can use it by capacity feeding, and I can just show you quickly that how interestingly you can get the benefit in terms of the cross-polar radiation. So even single probe, we can do some techniques so that the cross-pol goes down. The ground plane shaping was basically worked in 2000, early 2002 by Professor Wang and his group, where you can shape your ground plane, but definitely it is going to give you some bulky shape. Again, we are coming to the ground, that is the ground plane, but here the engineering is simpler because we are going to implement some strategic defects. And that was introduced in 2005. And here we just implemented one very simple small defect beneath one circular patch. Here the defect. The aim was to address the orthogonal mode. Because we already had this knowledge of this orthogonal mode or the higher order modes in the orthogonal direction. So how to kill this mode? So over the period, different shapes, different geometries, different experimentation have been reported. And it is now one industry qualified designs you get, and it is applied to different applications. That is another kind, the last kind of thing, that is the higher mode discrimination. Actually, all are based on the typical mode that is going to hard. The hard mode discrimination, the engineering is very simple. That is, you just parter the cavity boundary by just 3 and 3, that is 6 pins. What's the benefit? The orthogonal mode which is occurring, you can stop that mode from here. So you are free from this unwanted mode, then only one mode is present. The problem is that here you are going to parter this boundary, and definitely it is trying to do some changes in the resonant behavior. But more than 15 dB separation, very, very reasonable separation we get over the orthogonal plane. So more or less we are happy with this type of techniques and engineering. So I'm now going to present today another one. The concept is definitely a patch is a resonator, and it is a resonator for the dominant TM10 mode. But the same patch is no more considered as a resonating structure to the higher order mode and orthogonal mode, and it is behaving as a meta element. The idea and the aim I'm going to share with you When you deal with one microstrip of rectangular patch, it is the resonant length. TM10 is your desired mode, but you cannot stop this higher order mode or orthogonal mode because it is generated from the perturbation. This is the desired copolar radiation, that is the cross-polar radiation. And we propose that TM10 is our expected mode, so it will be there, but definitely we don't want with us this mode any further. So further this mode. But we are not going to use the techniques of ground, probe, or the cavity perturbation, nothing. Then what's the insight? Insight is very interesting if you look at here. For this mode, your center electric field is 0 and current becomes maximum. The very fundamental concept. For TM02 mode, your field is maximum, so E is max and current becomes 0. So just opposite requirement at center. So with this basic bounded, your basic understanding, now what's the approach? The approach is very simple for us. We are just going to introduce one single pole on top of this patch. The length is lambda by 4. The physics of lambda by 4 is not very complicated, but you will see the results very interesting. You consider any lambda by 4, that is quarter wavelength current path, you will see its input impedance is equal to 0. It has to be 0. So only this simple principle is being used. Now you see. What happens when you introduce just one small lambda by 4 on top of the patch? You look at this, your central field is 0, the surface impedance 0, its input impedance requirement is 0, so there is no change. That means TM10 will remain unperturbed. The mode cannot see that there is some foreign body. Come to TM02. Hopefully you guess it. You just look at very carefully. The electric field distribution is different, so fields are redistributed. Do you really believe it or not? Let's see. A noticeable change at center. The picture is very symbolic. That one red apple is visible within this green one. So look at exactly on the central line of a conventional patch. You're going to invite one higher, when you excite this higher mode, you see, it is the orthogonal mode central axis. You look at the center, but the pole is present. That field is vanishing, absolutely 0. Okay. Let's proceed further. You see the surface current. Surface current has to be 0 at center for a conventional patch because we are exciting 0 to mode deliberately. Is it really so? No. Current is propagating to this pole. So current distribution is shown through blue and red is the field. So redistributed field, it is under the control of redistributed current distribution. Now you see how do they influence the radiation, their performance. This is one conventional microstrip patch. When you are exciting it with TM10 mode, it is its radiation, cross-pol radiation pattern. Now you use this simple pole on top of this. You just visualize the nature of its cross-polar radiation. I'm showing here only the cross-pole. That is in magnitude, it is reduced, but it is scale is same. So reduced, it is reduced by 11 dB, and diagonal plane it is reduced by 4 dB. That means you are going to stop generation of that culprit, that the orthogonal disturbing mode. But the question is, so far we have considered, always we are using lambda by 4. What happens if we change the length? You look at very carefully. It is lambda by 4. It is lambda by 2. Actually, this is the resonance of the dominant mode, and this dominant mode is not being touched by this. So it is touching, influencing which one? The orthogonal mode, which is very weak. It is auto-generated due to perturbation. And the signature is here. You look at 15 dB separation, that is the red color. The red color is equal to lambda by 4. So our conjecture or our physical interpretation is absolutely perfect in offering this value. Good. You see the experiments, what kind of promise. This is E-plane, and interestingly, you just note the separation of the order of 11 dB through experiments. So that is highlighted by this red color. That is the final confirmation. Fine. That means this is the meta element for the higher mode, but it is the element or resonating element for the dominant mode. And you are not involving any complication in design or fabrication. You just take one piece of wire and solder it on the patch center. So your work or your engineering is done. Well, but the complete application. So you have taken one simple configuration where 4 probes, 4 elements and profit elements are there, the meta elements. Just you look at their performance. I'm going to show you very quickly. That means we're comparing when the 4 patches are there without this pole, and when the patches are there with this pole, that is the meta element configuration. There is no change in resonance. There is no change in the mutual coupling between 1 and 4, that is the H-plane coupling. Interestingly, there is a big difference, a considerable difference in the coupling parameters in E-plane. That means the poles carrying current, they are mutually interacting. So this is one engineering issue that has to be resolved. The problem is open to all. And the result, in terms of its radiation, you see, it is reflected. The basic pattern and gain with and without the spin or pole is the same. So only this little bit increase in the side lobe. It is due to this E-plane mutual coupling. But the remarkable, interesting part is the 12 dB separation in its cross-polar value. And that you can visualize from its simulated portrait, significantly reduced when you're using this meta element scatter. And that is the purpose of using meta element, that just by inserting this, you are going to improve this one. I'm going to mention just a couple of things that the engineers may not like, that only on top of this you are adding one very sleek, although very slick pole. Question is, can we short this, grounded it? Just you through this like a via and shoulder over here. Of course you can do it. It is simple, no one is going to stop you. It is hassle-free, very easy to fabricate, so you can short it. And it is sturdy, very robust. Question is, are you going to change its characteristics? You can understand, so I'm just going to show you. So you're not going to change the characteristics. So all the same. But when you attach from the top, it is the best one, the easy one. But from engineering robustness or a hard component, if you want to make it, so you can do it. No problem. The performance over the band, you may think that whether it is working over the band or not, the red card is important, that the order of separation, yes, all over the band it is working within 2 dB range. And peak gain is very straight. So performance wise, it is perfect. So no problem with this. Little bit microscopic, very critical view. I'm going to show you that how do they work. If I change the dielectric constant of the substrate, is it working? Or if I change the aspect ratio of the patch, is it working? Good, look at here. For 1.3 aspect ratio, you are going to get your best result in terms of cross-polar separation. In terms of peak gain, 1.6 is the best one. That is the aspect ratio. That is W equal to 1.6 of L, W is equal to 1.3 of L. So our final recommendation that 1.6, although it is good for maximum gain, but you can sacrifice few dBs of gain, but you are going to have very good cross-pol separation. So 1.3 is the best one. So this is the idea. I just now explained with you. The idea is based on our very recent work, which is published this month only. So all related physics, calculation, all results you can see from this presentation, from this paper. And now this idea, that is the meta-element concept, it is open to you all to explore its huge potential to develop new technology or to develop newer ideas and newer geometries. Thank you all. Thank you.